Let me introduce you our research leveraging sensitivity analysis for configuration Kafka cluster and multiple object model to minimize the latency. IoT devices, sensors, and variable sensing devices have become the data sources for construction project. Consequently, the architecture of such system had changed, and in the data ingestion layer, it included Apache Kafka cluster. In the architecture, Apache Kafka cluster emerged as a favorite solution due to its ability to provide speedy transformation, handle large volume of data, and ensure system resilience in the face of failure. However, Kafka is being extensively configurable and flexible system, and the uncertainties related to the proper configuration, selection of a proper configuration can negatively impact the performance of Kafka cluster. And under performance, we first of all consider the latency, end-to-end latency of Kafka cluster, which is defined as a time taken between the producer send data and consumer receive data. The motivation for our work is that despite its importance, the selecting an optimal Kafka configuration remains a challenging task. The challenge involves dynamically adjusting the configuration to prevent overloading or to maintain the high availability and low latency. Existing studies often focus on improving a single performance metric such as robustness and overlook other configurations. Consequently, this can lead to suboptimal or fragile configuration that do not generalize well for the real world deployment system. The goal of our research is to design a multi-object model that optimizes Kafka configuration to minimize end-to-end latency while quantifying independent parameters, influence, interaction effects, and the sensitivity to local parameters changes. The novelty of our contribution is a formalized optimization model that integrates global and local sensitivity indices to execute Kafka configuration tuning to prevent overloading while minimizing while maintaining high availability and low latency. Our formalization to formalize our model, we consider the global and local sensitivity indexes, and here is the first order Sobel index, which estimates how much of the output variance is due to input of a single parameter. Then Morris method measures sensitivity of the output using two metrics. In our research, we only use first metrics, which is the mean absolute elementary effect, showing the overall importance of a parameter, and then so-called Delors index that approximates the partial derivative of the model output with respect to the input at each point. Our multi-object model aims to find the configuration that minimize Kafka latency, as mentioned in equation number 8, while considering the combined effect from independent influence of a parameter with the sensitivity of latency to the local change, equation number 9, and the combined effect from influence of a parameter through interaction with other parameters, and again the sensitivity of latency to this change. We have added the expression defined by equation 9 and 10 as a penalties to our goal function, and this help us to define the multi-objective function and the model. And then in this model, we also use so-called adjusted ways to control or to balance the contribution of penalties on our goal function. Each parameter for this model is expressed by the interval of possible values. The magnitude of the weights that are included in the proposed model we measure with a Spearman rank correlation coefficient that we calculated between Sobel first index and Morris mu to determine this the global impact of a parameter and then the sensitivity captured by Morris and how those two indexes are aligned with each other. And then the second, we use a Spearman correlation coefficient between Morris mu and the Delors to determine how well the linear component of sensitivity expressed by Delors align with a local effect identified by the Morris. And then we created sort of like rules that state the following. When Spearman rank correlation coefficient between two sensitive indexes is high, so basically higher than 0.7, then information captured by both indexes overlap, and then we need to increase the values of we need to decrease the value of weights. When the Spearman correlation coefficient value is modern, then the correspondingly weights must be adjusted like on the model level, modern level. And for low correlation value, we do not put any adjustment on the weights which are used in our model. Then to solve the proposed multi-object model, we consider the optimization, the minimum optimization search algorithm. And we propose the adaptive optimization search strategy to take into consideration gradient-based and non-gradient based algorithms due to the next reason. The first reason here is that difference between the latency calculated for the optimal configuration using the so basically we form the criteria in order to select the best algorithm that to be used with the model. And those criteria are two. The first is the difference between the latency value calculated for the optimal configuration found with our model must be, and the latency predicted by the machine learning algorithm XGBoost regressal must be less than 1%. And then the minimum time complexity of the optimization method is selected by the number of iterations that were needed to complete the search. Then in our adaptive optimization strategy, we included algorithm. The first is limited memory, BFGS with bounds algorithm that handles optimization problem for a large database. This database with a features more than 100 by approximating the inverse Gaussian matrix of the objective function. Next is a sequential least square programming method that is an iterative optimization algorithm where on each iteration is solve the quadratic programming problem to generate a search direction. And this algorithm find the solution by approximated Gaussian matrix by Lagrangian function, not by the objective function as of the previous one. The complexity of the quadratic problem that is solved on each iteration makes this algorithm to be used better with a moderate dataset, the number of which less than 50. Then we included a trust region constraint method, which is a gradient-based optimization algorithm that find the solution by approximating again with a Gaussian matrix, approximating the objective function. However, step in each direction is accepted or rejected depending on the additional evaluation criteria, and this evaluation criteria is a ratio between actual and model function. So if this ratio is improved, then the step in the direction is accepted. The trust region constraint method is practical for moderate database. Then next is derivative-free method, PowerWell. It uses a set of direction, and then in each direction, using the parabola function through the 3 sample point in the direction, it selects the point that correspond to give the minimum of the parabola function, and then having this point, it calculates the next point and the direction. Having obtained the next point and the updated direction list, PowerWell continue the move to the next iteration until the optimal is found. Finally, the needle meat algorithm is a derivative-free method for minimizing real value function. The method starts with ordering and labels the simplex vertices such that function value are non-decreasing. And then the algorithm finds the direction, search direction using such terms as a reflection, expansions or expansion step, outside construction or inside construction, and finally shrink. On the picture on this slide shows how the directions are formed by the search direction are found by this method, and it is visible that unlike PowerWell, which search direction always the along search points along the fixed direction, here we can see the diversity, and due to this feature included in this algorithm, it is good for a dataset with noise. On this slide is specify an algorithm in a pseudocode of the adaptive optimization search strategies that we propose to find the Kafka cluster configuration. The input parameter of the algorithm is the Kafka cluster configuration parameter value defined in the internal, which is noted by the bounds, and then the method that accept the list of minimum search optimization methods that suggested, and then as a model, the algorithm suggests that the machine learning model that is going to be used for verification. This is the input parameters. The output parameter is a rank list of optimization algorithm, and as I mentioned, ranking is done by 2 criteria. This is a percentage difference in the latency and the number of iteration, which is we call like a time complexity of the algorithm. Then the body of algorithm starts from the line 3 to 8, where is performed sampling, modeling, and sensitivity analysis for each test scenario. Then in line 9 and 10, the calculated values of Delors and Morris indices are scaled to make them compatible the values to make their values compatible. Then in lines 11 and 12, a Spearman correlation coefficient is calculated in the weights for the multi-objective model are adjusted. In line 19 and 20, general purpose optimization function minimize from the Python library optimize is called. The parameter passed to this function include developed by us the function called objective value that implements the multi-objective model. Then X0, the initial configuration of a Kafka cluster randomly selected for the start iteration. Then the calculated values and scale by sensitivity indexes, Delors, Morris, and Sobel indexes, finally adjusted weights, and the list of the optimization search algorithm. In line 21, the Kafka cluster configuration found by completed optimization search, and the corresponding latency is received as well, and those parameters are stored in so-called result list. In the block 2428, for each configuration in result list, the predicted latency is obtained using the given machine learning model, and then percentage difference in the latency value is calculated and stored in the variable so-called error score. And finally, in line 29, the ranking is applied based on the keys, error score, and number of iterations. This was the theoretical part of our research, and now we move to the experiment part with starting to preparation of a data set for our experience. And to collect the data set, we defined 5 scenarios to test Kafka cluster under different situation. And first scenario is to test Kafka cluster latency with high throughput, emphasizing with durability. A second, to test Kafka latency with low latency and average throughput. Then scenario number 3, to measure Kafka cluster latency with a balanced throughput and latency with a fault tolerance. Then scenario number 4 is to measure the latency with a stress test, and the final scenario to measure latency with a high fetch size for the bulk processing. Then each Kafka cluster parameter that we included in the test we specify using the notation. And this is basically 3 terms: the name of parameter, then the possible value specifies a linguistic term, and finally the for each state, right, of the variable, we specify the internal with possible values. Then we associated the defined scenario with a state of each Kafka cluster parameter, and then data set consisting of 1,000 of observation had been received as a result of running 200 times each scenario with the proper configuration and the telemetry data sent from EOT device HOBA-MX100 every second. The size of each message is 387 bytes. And then we include the implementation of a search algorithm that we included in our experimental was from the Python library Optimize. For verification, as I mentioned, we use a XGBoost regression model trained on the collected data set, and the quality of the model was received so that the determination coefficient is 83%, indicates that the model captured the majority of variance in the data set, and the mean square error less than 1%, indicating the predicting accuracy. This slide, as a result of our experiment, we received the sensitivity indexes for each parameter in each scenario. And analytical analysis of this result help us to conclude the following. First of all, each parameter has a different degree of influence driven by the independent impact or impact through the interaction of these parameters with other parameters. So we haven't found any single parameter which is equally impact the latency by estimated by all three indexes. And then we found that combined effect of a parameter as a result of interaction with other parameter dominates both others. So basically dominates the independent influence and its sensitivity to local value changes. This sensitivity analysis results gave us the understanding that the data set basically has a lot of interaction between parameters, right? And this we understood from this sensitivity analysis. Then the result of the optimization search is presented on the current slide in the table, and in the column objective latency is listed the value of latency found by each algorithm for each sensitivity for each scenario. The number of iteration is listed that required to complete the search is listed in the column search iteration. And the predicted value of latency by machine learning model is listed in the column predicted latency. The difference between the values calculated latency and the predicted latency is specified in the column latency difference. The analysis of the result show us the following that first two method like LBFGS with bounds and SLS-QP consistently converge within 10 iterations across all scenarios. However, the configuration found by those algorithms did not yield optimal latency. The resulting latency exceeded the predicted values in all scenarios. Then again, the derivative-dependent algorithm trust region constraint require a moderate number of iterations. So it's sometimes this 20, sometimes 100 iteration, and demonstrated less than 1% difference between the objective latency and the predicted latency in all scenarios. And finally, two last methods, which are non-gradient based method, Powell and Needle Mead, achieved similar final objective latency as the trust region constraint with a very small deviation, less than 1% from a predicted latency. However, those methods require a significant more iteration, and it's up to 598 for Powell and 397 for a Needle Mead, indicated that with this method we do have a trade-off between accuracy and computation efficiency. We analyze, as I mentioned, the reason why with the first two derivatives, the gradient-based method, we didn't succeed, and our understanding is here the following, that LBFGS with a bound method as well as QP method assume that objective function has a smooth curvature. They tend to converge premature to suboptimal region because in the data set, based on our sensitivity analysis result, the optimization landscape is not linear. So those first two methods had failed. The trust region constraint method overperformed in this study because its ability to dynamically adjust the gradient step, as we saw, when the predicted improvement deviates from the actual improvement. This adaptive behavior of a trust region constraint helps to avoid premature converge, as illustrated by the green line on this picture. And Powell and Needle do not rely on gradient information, so they explore parameter interaction through multi-points evaluation, and they produce accurate results, but require more iteration to complete the survey. On this slide, it shows how the different configuration had been found by three succeed in this study method: trust region constraint, needle mid, and power well. Such behavior implies a level of redundancy or flexibility in configuration tuning, where alternative configuration may be selected to meet secondary objectives, such as, for instance, operation constraint, without significant impact of latency. In this context, the design multi-objective model serves as a valuable tool to guide the configuration selection process by quantifying and incorporating such secondary objectives into the optimization landscape. In the conclusion, we propose a multi-objective model that optimizes Kafka cluster configuration to minimize end-to-end latency, and quantifying independent parameter influence, interaction effect, and sensitivity to local parameter changes. We propose an adaptive strategy to search the optimal value. The validation of the received result was done against the prediction of the trained XGBoost regressive machine learning algorithm, and revealed less than 1% latency difference for trust region constraint method, Powell, and needle mid algorithms. Overall, the proposed multi-objective function validated by machine learning prediction and tested across multiple optimization strategies offers, in our opinion, a robust and practical tool for Kafka performance tuning. Future work will be explore how to integrate the proposed multi-objective function into dynamic optimization framework suitable for real-time deployment and scaling scenarios. Thank you for your attention.